Bismillahirrahmanirrahim. I hope every one of you will be all right. Yesterday we finished Borax. Continuing the same chapter 3, I start with boric acid. Important boric acids are, we have four important boric acids, namely orthoboric acid, formula H3BO3. There is another way of writing it, B2O3 plus 3 add, having 3 water molecules. Second, metaboric acid, HBO2, we can also write it as B2O3 and single water molecule. The third boric acid is tetraboric acid, H2B4O7, can also be written as 2B2O3 and water molecule. Fourth is pyroboric acid, H6B4O9, it can also be written as 2B2O3 and 3 water molecules. So these acids, these are four acids which are interconvertible. One boric acid can be converted into another boric acid. So first is conversion of metaboric acid into boric acid. Metaboric acid treated with water, boiled, and then allowed to crystallize, so it is get converted into orthoboric acid. The second conversion is conversion of tetraboric acid into boric acid. H2B4O6 plus 5 water molecules, and then we get orthoboric acid is obtained. Orthoboric acid, or also known as simply as boric acid. Now we are going to prepare and look into the properties of orthoboric acid, which is simply called as boric acid. First of all is preparation on commercial scale. First method is from columenite. On commercial scale, boric acid is prepared by boiling ore columenite. It means columenite is a natural source in water, and then sulfur dioxide is passed through it. Boric acid crystallizes out from the solution while calcium sulfate remains in solution. The equation of the above reaction is columenite Ca2b6O11 plus 2 sulfur dioxide and 9 water molecules. They react to give you calcium sulfate, and orthoboric acid is obtained. The second method is from borax. A hot concentrated solution of borax on treatment with calculated quantity of concentrated sulfuric acid produce boric oxide, which is crystallized out on cooling. So the equation is, this is borax and A2B4O7. We have studied it yesterday. Calculated amount of sulfuric acid, little water, and it gives us sodium sulfate and orthoboric acid. These are the two available methods for the preparation of orthoboric acid. Now are the physical properties. Physical properties, it is white, lustrous, crystalline solid. It is white, lustrous, crystalline solid with a soapy touch. Soapy touch means slippery. It is slippery to our hands. Second is solubility. Solubility is very less. It is only 2.6% soluble at 40 centigrade. But it is 37% soluble at 107 centigrade. So solubility varies with the rise in temperature. At high temperature, it is more soluble as compared in a lower temperature. Third, it is volatile in steam. In steam, it is volatile. Volatile means it is converted into vapors. Then we come to the chemical properties. First is reaction with alcohols. With ethyl alcohol, it forms ethyl borate. Water alcohols, those organic compounds which contains OH group, they are called as alcohols. This is ethyl group C2H5. It replaces all the three hydrogens of orthoboric acid. And so that with the replacement of these three hydrogens by C2H5, we get C2H5 3BO3 plus 3 water. So that will be called as ethyl borate. Then is action of heat. Important one, action of heat can be studied in the following steps. Orthoboric acid, when heated, it gives metaboric acid plus water. So one molecule of water evaporates out. H2O goes out, remaining behind HbO2, which is termed as metaboric acid. If it is further heated, then four molecules they combine together and eliminate water molecules. As a result, tetraboric acid is formed. This tetraboric acid, on further heating, produces boron oxide and water. Boron oxide and water. Then is orthoboric acid is a very weak acid. The strength of an acid depends on the number of hydrogen ion produced. Those acids which produce large number of hydrogen ions, they are considered as strong acids. While those acids which produce very few hydrogen ions, they are called as weak acids. So orthoboric acid, when we say it is a weak acid, it means it produces very few hydrogen ions. How it produces? Orthoboric acid plus water. We know water is HOH. The OH part of the water is absorbed by boron and hydrogen ion is released. It is the ion of the water which creates acidity in it. It has no effect on methyl orange. The another acidic character is that the color of methyl orange changes with the acid. The acid is so weak that it has no effect on methyl orange indicator, but turns blue litmus red, which is an acidic character, and thus acidic character is indicated. It is partially neutralized by caustic soda to give borax. So orthoboric acid reacts with an alkali to form salt borax sodium tetraborate plus 7 molecules of water. So these are the 3 points which prove the acidic character of orthoboric acid. Now fourth, reaction with soda ash. Soda ash is dry sodium carbonate. Boric acid is neutralized by soda ash sodium carbonate, which is also a weak base. So as acid, base, they react to form salt, sodium tetraborate, water and carbon dioxide. 4 molecules of orthoboric acid, 1 of sodium carbonate reacts to give us borax plus water and carbon dioxide. It can also be it can be titrated with alkalis in usual, it cannot be titrated with alkalis in usual manner. However, it can be titrated against standard alkalis using phenolphthalein as indicator. Standard alkali means whose strength is known, and phenolphthalein is an indicator which indicate the change of the media, whether it is acidic or basic. But water is not to be used, it is in the presence of glycerol. This everything will happen when glycerol is the solvent. Uses of boric acid. It is used in medicine as antiseptic and eye wash. Antiseptic means which kills germs. Number two, it is used in pottery as a glaze. The earthenware vessels which are to given a slippery touch or glaze, there it can be used there to make the pottery as a glaze, to make it slippery or to make it non-absorbent for the water and other liquids. It is used in the cattle industry for stiffening of wicks. For stiffening a wick, you have the thread which burns in the candle. It is as this acid is used to make it hard so that the flame remains erected. So we finish boron here and start aluminium, the second element of the third group. Aluminium, it is reactive metal. It is coated with a layer of aluminium oxide. The oxygen of the atmosphere slowly reacts with the surface of the aluminium to form aluminium oxide, which protects it from further corrosion. This aluminium oxide is very hard and it adheres to the surface of the aluminium, so further decay of the aluminium metal is avoided. So we can say it is a protective layer which prevents further attack or further wastage of the metal. The oxide layer is made thick by electrolytic process called anodizing. In order to make it more preventive, we want to thick this layer, and for this the process used is electrolytic process, and the particular name is anodizing. Number two, aluminium on heating with hydrogen forms aluminium hydride. So it reacts with hydrogen. On heating, aluminium reacts with hydrogen to produce aluminium hydride, AlH3. The 3 is the valency of aluminium. Third, oxide formation. Burning of aluminium. Aluminium burns in air at high temperature. The reaction is accompanied by evolution of heat. It is a highly exothermic reaction. Large amount of heat is liberated and is accompanied by evolution of heat and intense white light. It produces white light, which in the olden days it was used as a photographic during the night, and the reaction is 4 aluminium plus 3 oxygens giving us aluminium oxide plus energy, both heat and light energy is also given. Then next reaction is oxide formation, then is reaction with nitrogen. When aluminium is burned in air, in addition to oxide, white aluminium nitride is also formed because nitrogen is also present along with oxygen. So nitrogen also react with aluminium to produce aluminium nitride, which is a white color. Then is reaction with halogens. When halogens are passed over heated aluminium, aluminium halides are produced. Halides are the salts of halogens. Very simple, 2 aluminium plus 3 halogens give us aluminium halide. Then is action with acids. Important one as regards the examination point of view. Reaction with acids. With first of all dilute acids. Aluminium dissolved in dilute acids to give hydrogen. So similar to other metals, aluminium plus dilute HCl reacts to form salt of HCl, aluminium chloride plus evolution of 3 hydrogens. Likewise, aluminium reacts with sulfuric acid, producing aluminium sulfate and hydrogen. Dilute nitric acid reacts slowly without evolution of any gas. So, no evolution of hydrogen. Unlike the other acids, it produces ammonium nitrate. So, the equation is 8 aluminium, 30 nitric acids, aluminium nitrate, and ammonium nitrate, which others are not producing it, and 9 water molecules. Now, after dilute acids, concentrated acids, they put concentrated sulfuric acid produces sulfur dioxide with aluminium. Aluminium plus concentrated sulfuric acid in hot state. We get aluminium sulfate and sulfur dioxide plus 6 water. Seventh is reaction with caustic soda. Reaction with caustic soda, aluminium dissolves in aqueous alkalis like sodium hydroxide, potassium hydroxide. The reaction is again very important. 2 aluminium reacts with 2 sodium hydroxide. In presence of water, we get a salt NaLO2 plus 3 hydrogen. Hydrogen is eliminated. The compound form is called as sodium aluminate. It is known as sodium aluminate. That finishes aluminium. Now we start with group 4. The third group is completed and fourth group has following elements. Number first, at the top of this group is carbon, 6 electrons, atomic number 6. Silicon, Si, 14 electrons, so atomic number is 14. Germanium, atomic number 32. Tin, atomic number 50. And lead, atomic number 82. Its electronic configuration is the outermost valency electron has 2 electrons in the s and 2 in the p orbital. All of them. Only principal quantum number will change. The electronic configuration resembles 2 in the s, 2 in the p. 2 in the s, 2 in the p. So this is electronic configuration. Carbon 6, 1s2, 2s2, 2p2. So in the outermost electron, 4 electrons. Silicon, likewise 1s2, and in the end, outermost orbital, it has 3s2, 3p2. Germanium, 32, it goes like this, 4, principal quantum number 4, in the outermost shell, 4s2 and 4p2. So again 4 electrons. Tin, proceeding through all these, and on the outermost shell we have 5s2, 5p2, 2 electrons plus 2 electrons at 5 level. Principal quantum number we have 4 electrons. Likewise, lead has 6s2 and 6p2. So the outer shell consists of ns2 and p2. It can be any number starting from 2, 3, 4, 5 and 6. We have s2 and p2 electronic configuration. Electronic configuration can be easily written as like this if we take help of the noble gases. So noble gas, this is the kernel. The kernel is of helium. Carbon is 6, helium plus 2 electron here, plus 2 and 2, 4. It will make 6 electrons. Neon, it has 10. So 2 or 2, 14 electrons. Argon, 18 electrons, 3d10, 4s2, and that will make it 32. Likewise, 5s2, kernel is of krypton, kernel is of xenon, and we have 6s2, 6p2 in the lead. Carbon. So the time is finished and we finished it over here. ठीक हो गया?